Okay, thank you for the introduction. So first of all, I'd like to thank the organizers to giving the opportunity to talk in this nice workshop. So this talk is going to be about some very recent work. Well, we already have some results, and we are actually collecting more, and we are about to write the paper. But I found the result very interesting, so I decided to talk about this in this workshop. It's not spin chains, but somehow related, because most I'm going to talk about field theory, because this Cardy's ansatz is actually an ansatz for for ground state of massive field theories, which can be seen as perturbations of conformal field theories. And this ansatz is written in terms of conformal boundary states. And I'm going to also talk about this left-right entanglement entropy, which is the entanglement entropy between the left and right movers of the CFT. So, okay, so just some very, very brief introduction. So as I thought, I'm going to talk about relativistic quantum field theories, which are actually related to spin chains, because when you have a statistical physical system and then you take the scaling limit, like you send the lattice spacing to 0 and increase the number of sites, and then on length scales, which are much larger than the lattice spacing, then these kind of systems can be described by relativistic quantum field theories. And then these quantum field theories, they have this renormalization group approach. And so like general field theory, you can consider like a point on a renormalization group flow or renormalization group trajectory, which have fixed points, which are characterized by so-called conformal field theories. So like roughly speaking, for me, like massive QFT and renormalization group trajectory or flow is gonna be the same, and I'm consider these things as perturbations of the fixed point of the theory. So like if you want to characterize a general massive quantum field theory, it's a very hard problem and generally requires non-perturbative methods. And in this talk, I'm going to talk about ground states. And ground states are interesting because they contain a lot of information about the field theory. Very important quantity is the ground state energy density, for example. And you can also get information about the phases of matter, because if you have some some order parameter, which is basically a local field in your field theory, and then you can ask whether if the one-point function of this order parameter is 0 or not. So you can characterize phase transitions with this. Entanglement properties are also very interesting, because there are some phase transitions which are of particular interest, which don't have order parameters, but the phase transitions can be characterized by the entanglement properties of the ground state, basically. Just some technicality. Like this talk, I'm going to talk about 1+1 dimensional field theories and basically massive perturbations of conformal minima models. It's like, just to recap what we know about about QFT in general. So let's say generally, if you have a very general massive field theory, let's say not so much. But if you have some extra symmetry, for example, conformal symmetry, and you consider conformal field theory, we know a lot about these kind of theories. So for example, there is operator product expansion and the conformal invariance. Using these two things, basically you can, in principle, calculate any endpoint functions. Like you use the OP and then you reduce to one-point functions, basically. Also, like related to entanglement entropy, is also some recent developments on this twist field approach and replica tricks. So using these twist fields, you can calculate real space entanglement in these theories. And of course, there are many, many other results. If you go away from criticality, so you leave the critical point, but you still can have some very large symmetry, which is integrability. So if you have an integrable field theory, you also know a lot about these kind of theories. So the spectrum of these theories are known. It's called basically the S-matrix bootstrap problem. And then also finite size effects are characterized by thermodynamic beta ansatz and its relatives. 1-point functions and form factors are also can be calculated in these integrable theories. So, and using this, you can also write down some, let's say, formal expansions of any m-point functions. Also, twist-weight form factors are recently, the theory of twist-weight form factor are recently worked out. So you can calculate the entanglement entropy in these theories as well. And of course, many other results. And I said generally we don't know so much, but based on these two, you can consider other general field theories as perturbations of these two. Now you can use some CFT perturbation theory or form factor perturbation theory to study these problems. And also there are some numerics which I'm gonna show you. So this is the brief outline of the talk. So I put this in this logical order. So first I'm gonna talk about Cardy's ansatz, and then left-right entanglement entropy, and then this numerical method which is called truncated conformal space approach. And then I'm gonna conclude. But actually first I started to play with the TCSA, the truncated conformal space approach, and I started to study this quantity, which turned out to be studied in some sense, and it's called left-right entanglement entropy. So we realized this this literature, and then actually Gabor pointed out this recent paper of Cardy about Cardy's ansatz, and then with that we could put these results that I got from here in a general context. So at the end I'm gonna conclude. So let's start with Cardy's ansatz. So what is the problem that I'm gonna study? Like let's consider some perturbation of a CFT with some relevant perturbations, and these perturbations are spinless fields in order to respect translation invariance. So this is the Hamiltonian. You have the CFT Hamiltonian and these perturbations. So this is the general problem of, let's say, massive field theory. And the question is, like, what is the ground state of this Hamiltonian? And there are some indications which I'm gonna briefly discuss soon, that these ground states can be characterized by the boundary states of the CFT. And all of these things about Cardy's ansatz can be found in this paper, this background normalization group rules and boundary states in CFT from last year. So let's talk about these indications that say that the ground states of this Hamiltonian can be characterized by the boundary states. So first imagine that you consider your theory on a wall plane, and you cut it to two halves, and then you turn on this massive perturbation only on one half of the system. So and then you have an interface between a massive field theory and the conformal field theory. And then if you see this from the CFT side, what you're gonna see is that that there is some boundary condition on your conformal field theory. And then based on Cardy's earlier work, that these boundary conditions in CFT, they flow under the renormalization group to some boundary, some conformal boundary conditions. So Cardy says that if you are on the CFT side, and then you are, in this case, close to the boundary, that the correlations that you see, they basically should be somehow the same as some irrelevant deformation of a conformal boundary state, because the boundary condition flows into a boundary fixed point. So if you're out of this fixed point, that can be considered as an irrelevant perturbation of that fixed point. And the second indication is from last year. It's Joe, Ludwig, and Ryu, where they studied the entanglement Hamiltonian. So the entanglement Hamiltonian is the following: you take your system, you cut it to two halves, and then you calculate the reduced density matrix, let's say the left part, which I call rho A, and you can consider this as an exponential of some Hamiltonian, which this Hamiltonian is called the entanglement Hamiltonian. The spectrum of this Hamiltonian is called the entanglement spectrum. And what they found that the entanglement spectrum in massive field theories, they are related to the spectrum of a boundary CFT with some very special boundary conditions. Let's say free boundary conditions on one side and a special boundary condition on the other side, which depend on the perturbation that you use in the back. And this result that they found, it's also supported by some numerics. And the last indication is based on the work of Cardy and Calabrese from 2006, where they studied quantum quenches to or close to critical points. And they studied the correlation function in this system, and they used the path integral approach. And then when you do the path integral, like you should put the boundary conditions, which are the exact ground state. But instead of that, they used some regularized bound state, and they could get the correct results for the correlation functions. Okay, so based on this indication, Cardy wrote this ansatz. So he says that the ground state of the massive field theory can be written as a linear combination of this regularized boundary states. So these tau's are the so-called regularization parameter, and H CFT is the CFT Hamiltonian that you take the perturbation of. And these A's are Cardy states, which are a very specific linear combination of so-called Ishibashi states. So you take this ansatz, and then what you have to do is to minimize this energy density in large volume. So this whole ansatz is valid in large volumes, large system size. Okay, so when you carry out the calculation, well, okay, so these are the Cardy states. These are very specific linear combinations of Ishibashi states. Which Ishibashi states are linear combinations of this form. So you take leftovers from the Virasoro module, and then you take this linear combination. You only get states from the same level and from the same module. So this is called Ishibashi state, and then this is the state that you put actually here. And then you have as many states like this, as many Verma modules you have in your Hilbert space. Okay. So if you take this and you start to do this calculation, it turns out that this Hamiltonian actually acts diagonally on these states. So like for each Cardy state, you have a different energy, which is like this, and you have to minimize this. C is the central charge of the theory, and these are the modular matrix elements which characterize the transformation of Virasoro characters under modular transformations. And these deltas are the conformal weight of the perturbation that you use. I just want to say that there is a 4 here. In the paper it's 2, but I think there is a typo, and but I can show it to you why I think it's 4, and one other reason is that if you do it with 2, it's not going to work. Yeah, this is for the ground state. So you have, that's the thing I was going to say. So you calculate, you try to minimize each of them, and then you pick up the lowest one. So at the end, from this linear combination, only one survives. So there is only one alpha and only one tau. Okay, let's see if it works or not. So you can take some integrable examples, because in integrable field theory, based on the work of Fatyaev, you know like the ground state energy density. So if you set the lowest mass of the theory to 1, that's your scale, and then this is the exact results for the scattering theories E8, E7, E6, which are some very specific perturbations of very specific CFTs. Where? Ah, okay, so it means that C is equal to 1/2, and you consider this perturbation. This is okay, sorry. So this plus is it means that we use this perturbation. So we have the yeah. I mean, like you have the CFT plus perturbation. So this is the Hamiltonian, if you want. Okay, yes, Manta plus, exactly. Okay, and this is E8, and then E7 you have the tricriticalizing with this perturbation, and for E6 you have tricritical pots with this perturbation. Yes, it started, yeah. So the scattering theory and basically everything is morally known about these things. So if you use the formulas from Fatyaev, you get these numbers, And then if you do the minimalization procedure with Cardys, you get these numbers. No. See, so these are 3 different theories, and these numbers are the ground state energy density. Yes. The second one is tricritical easing plus this. And then tricritical pots, actually. So this is M3, 4, 4, 5, and 6, 7. If you want. This L means lowest, so this is the lowest mass of the theory. Okay, so these numbers are very good. So it seems that Cardy's ansatz captures the ground state energy density very well. You can take some other example, which is non-integrable, where you don't have exact results. But what you can do, you can use this truncated conformal space approach, which I'm gonna tell you later about. And then you can plot the ground state energy against the volume. And then you see there is some finite size effects, but in large volumes it's linear. And then this line is a line with a slope which comes from Cardy. So it works for non-integrable cases as well. Okay, but this was only about the variational energy. But he also says that the state is very, very specific. So let's try to get some information about the state, not just the energy density. So for this, I'm going to use this left-right entanglement entropy. Okay, just some context of this. So first, this was studied by Liha, Dane, and Kikatsura and Ludwig. What they did is they considered the gap topological states. And what they did in 2 plus 1D, and what they did, they cut the system into 2 halves, and then they calculated the entanglement properties between these 2 halves. And then in these topological states of matter, then when you have a boundary, then actually the edge excitations live on the boundary. And they give an interpretation to this when you cut your system to 2 halves, the 2 plus 1D system into 2 halves, then you have the 2 edges, which have these chiral edge modes. And they said that the entanglement entropy between these 2 regions can be characterized as the entanglement entropy between the left movers of one chiral edge and the right movers from the other chiral edge. Okay, and now I'm going to show some specific results for boundary states in CFT, which is a result from Das and Datta from 2015. So let's consider these kind of states. So you have some regularized boundary state. This B can be, at this point, any linear combination of Ishibashi states. You just cook this up, and then this normalization factor is given by the characters of the CFT evaluated in this very specific point. And there are also the coefficients of the linear combination. Yeah, so they studied the left-right entanglement entropy of this kind of state. Just to remind you that this is really like Cardy's ansatz. Okay, so the result is the following: like when you have this state, you can write down the density matrix in this left-right decomposition, and then you can trace out over the right movers, for example, and then you end up with the reduced density matrix of the left movers, which has this form. Yes, which has this form, and then use this. What they did, they calculated, they used some replica tricks. So they calculated trace of rho left to the power of n. They did some modular transformation, and they did this large L expansion. So this result also valid in large L as Cardy's ansatz. This is the result, which is kind of very simple. So there is a non-universal linear behavior the system size, which contains this regularization parameter tau. And there are some constants factors which can be written in terms of modular parameter. S is the modular S matrix. Yes. Ah, okay, which this S? Ah, no, no, no. So this S, okay, you're right. Yeah, yeah, this is the left-right entanglement entropy. Yes. So you consider, you take the density matrix written in this left-right separation, and then you trace out over the right movers, and you calculate phenomenon entropy. Okay. So in principle, so in particular, if this state that you use in this formalism is a Cardy state, which is written in again like this linear combination of Ishibashi states, then you end up with this very simple result. So this left-right entanglement entropy of a regularized boundary state, regularized Cardy state, can be written as this linear term, which is non-universal, and this universal term, which only depends on the modular S matrix of the CFT. Okay, and then we can ask whether if so if Cardy's ansatz is right, if you calculate this left-right entanglement of a ground state of a massive field theory, then it should be like this form, because Cardy says that the ground state is a regularized boundary state. But the question is how to get access to this, because well, you really need some information about the ground state of the Yeah, sure. Actually, this comes from Rényi entropy. So what they did is they calculate trace rho n, trace rho to the power n, and then they take n goes to 1 limit. I don't remember exactly. That it's written in this paper. I just use this result. So okay. So, and now here comes my numerical method, which is the truncated conformal space, where you can actually get these ground states. As I showed you earlier, that the ground state energy you can get. You also can get the state. So how this truncated approach works. So first it was used by Yurov and Zamolodchikov in 1990 for the scaling Lie model. And after that, it has many, many variations. So you can find like truncated Hamiltonian space approach, truncated conformal space approach. There's a truncated fermionic approach. Some people call this Hamiltonian truncation. It has many names right now. But the idea is very simple. You take your Hamiltonian and you write this as the following. So your Hamiltonian is some H naught plus some perturbation. And then let's say this H naught is very well known, meaning that you know all the eigenstates, all the energy levels, and then you can calculate any matrix elements of any operators. I mean, by very well known, I mean this. And it's very important that this Hamiltonian acts on an infinite dimensional Hilbert space, but discrete. For example, if you take your theory in finite volume, you have a discrete spectrum, okay. Which is very important because what we are going to do is like, instead of this Hamiltonian, we are going to study this projected Hamiltonian. So you take your Hamiltonian and then you take some energy cutoff, this capital lambda, and then you consider states with energy below this lambda. So in this way, you're going to end up with the finite dimensional discrete problem. And since these matrix elements are known, you can write down this truncated Hamiltonian of this problem, and then you feed it to your computer and then get some result which depend on the truncation. Actually, strictly speaking, this only works if the low energy modes which you keep, they're not they interact weakly with the high energy modes. Weakly, I mean, like these matrix elements are very small if M is a high energy state and then is a low energy state. Yeah, if in a CFT language, if the perturbation is relevant, which we like, it's the case. Okay, just to show some applications of this. So for example, you can get the finite size spectrum of perturbations of CFT. You can extract scattering phases of two particle scatterings. You can get access to the form factors. Also, there is a recent work of Gábor Takács and collaborators in Hungary that they calculated correlation functions using this approach. You can also do time evolution because you imagine you have some initial state, and then you have your finite dimensional Hamiltonian, you construct somehow the exponential of it, and then you can do any time evolution that you like. This is also done. There is a very nice result, actually, I like it, that you also can get access to the second Rényi entropy, like spatial. Yes, it means n equal to 2. But it's kind of involved, but it matches very well with form factor approach, with integrability. Okay, and there are some other renormalization group improvements, because you know that you always have this cutoff, but the exact results actually coming from the exact results come from infinite cutoff. But there are some RG improvements, like how you can modify your finite cutoff coupling in order to get infinite cutoff results. And there are some recent work of Slava Ričko from CERN that they studied higher dimension problems, not just 1 + 1. And then if you're interested, there is this nice recent review of James Connick, Lachemine, Robinson, and Zwelik, and then most of these things are discussed in this paper, and then if you need references, you can find it there. Okay. So what makes it truncated conformal space approach? So when you take your H0 as a CFT Hamiltonian, then it's called truncated conformal space approach, because you use the conformal space of states. So in general, you can just to mention that in this case, I'm going to talking about only diagonal minima models. So when you have Verma modules with left and right conformal weight being the same, and then you have all the modules from the Katz table in your Hilbert space. So this generally has this direct sum, but like formally you can embed this to a Hilbert space, which is like Hilbert space of left movers and right movers. Just many of the well, okay, let's say diagonal modular invariance of unitary minima models. So chirality doesn't do anything with unitary. So if you take, for example, Li Yang, that's a non-unitary minima model. But I only consider unitary minima models. Diagonal modular invariance of unitary minima models, to be precise. So like using Virasoro generators, like you can generate very easily the space of states of the CFT. And then using conformal word identities, you can basically calculate any matrix elements that you want. So in this sense, this H0, which is HCFT, is well known. And then, well, okay, and then we impose periodic boundary conditions, and then we take only spinless perturbations. So there is translation invariance, and then you can treat like different momentum sectors separately, which is very nice, because if you consider ground state properties, the ground state live in the zero momentum sector, and then you don't have to take care about other sectors, and it reduces the number of states that you have to use. So. And then we already discussed this a bit. Like the convergence properties depend on the conformal weight of the perturbation. So the more relevant the perturbation, the more fast the convergence is. So in this talk, I'm gonna use results with very, very relevant perturbations. So let's say you keep a couple of thousand states, and then basically the result is exact. Okay. Just to show you like a typical example that what you get from this stuff. So this is E8. So this is Ising model in magnetic field. And then I plotted here the relative energies against the system size. So you take, this is the system size, and this is the relative energy. So this is the ground state, which has relative energy 0, of course. And then you have these lines here. So these lines come from theory. So these are the first 3 masses of this theory. There are 5 more, but the spectrum is very dense in this part, so I just didn't put them. But you can see that that you can get the masses of the 3 lightest particles in this model. And in this case, I used, I guess, around 500 states. But because the perturbation is 1/16, so it's very relevant. Actually, the original paper of Yurov and Zamolodchikov, they used 19 states, and then basically you don't see much difference. Okay, so this is about energy, but when you do the diagonalization, you also have the eigenstates. So generally what you get the ground state, for example, the normalized ground state in this form. So you have some coefficients of this linear combination, and this you can see that this is a pure state in this left-right separation. And then when you have these numbers, then you can calculate basically very easily the reduced density matrix. And then after that, it's very easy to take the trace over right movers, for example, and you end up with the left with the left reduced density matrix, and then you calculate. At this point, you can calculate any Rényi entropies because these are just matrices of numbers. So, and then just to remind you, so this was Cardy's ansatz. Well, okay. Let's say formally, like you can take this row and then which is a matrix of numbers, and then you can have any function of it, and then you can just take the trace. Yeah, of course. Yeah. That I don't know. This is. Well, that I don't know. I never checked. But this is, let's say, brute force calculation. Like. Okay, no worries. Okay. So just to recap, so this was Cardy's ansatz. It's a regularized Cardy state. And for the result of this kind of states, like properly normalized, is this. And the only thing the only parameter is this tau, which you can get from the minimization principle. So you minimize the ground state energy density, and then which tells you which A you have to use in the linear combination, and then it also gives you the tau. And then you put that tau in this formula, and then this is what you get. So this is also again, so this axis is the system size, and this is this left-right entanglement entropy in the ground state. So the dots come from the truncated conformal space approach, and the line is this line with the tau given by the minimization principle. So as you can see that in small volumes, something happens. We don't know. Well, of course, we know that it has to start from 0 because small volume means that you are actually very close to the critical point, and the CFT ground state has 0 left-right entanglement entropy because it's just identity tensor identity, the state. And then it starts to grow, and then it has this linear behavior, and then if you put the theory based on Cardy's ansatz and the result for left-right entanglement entropy for boundary states, then you see basically perfect match. And this is in A8, integrable model. Okay, you can also do this non-integrable perturbation, for example. This is now tricritical Ising model perturbed with this 3/80 perturbation, and then basically you have the same nice behavior. But actually, so the conclusion here is that it seems that Cardy's ansatz is really a good ansatz for the ground state, based on this left-right entanglement entropy. But actually, you can go even further. So if you remember, like the form of the reduced density matrix, when you trace after tracing out the right movers, for example. And from this, you can read off the entanglement spectrum, basically. This okay. So this is a summation over modules, descendant levels, and states on a given level. So n is the descendant level. So you can read off the entanglement spectrum of this left-right entanglement spectrum, which depends on like these coefficients of the linear combination, which in our case is just the modular matrix elements. This normalization, it comes from some linear combination of characters evaluated at a certain point. So this actually also has L dependence. It's hidden inside, and this is actually very similar to the usual entanglement spectrum of Ludwig and Cho and Ryu. And then you can do this plot. So this is again like these are the first 6 levels of the 6 energy levels of the entanglement Hamiltonian, because you have the reduced density matrix from the truncated conformal space approach, and then you can take the eigenvalues of it. Like. Yeah, that's a good question. Actually, this goes on. So there are many more lines here, but and then if you see like this behavior, it's well in small volumes it's not good, but that's okay because both Cardy's ansatz and both the results for the left-right entanglement entropy is valid for large volumes. And if you see like in large volumes, it gets better and better and better. And I think if you go to higher and higher and higher volumes, and then you keep doing this, then I think you will see the degeneracy, I'm pretty sure. So these lines actually are coming from this formula. So the first formula is comes from the identity, so age is 0, level 0. Yeah, that's true, but yes. Yeah, in principle, the degeneracy you can read off from this case, because this case run on a given level of a module. So, well, if it really works out fine and then you go to very high volumes, I think you can count the number of states from CFT. That's what I'm trying to say. But so this first line, for example, this thing here, this comes from the highest weight vector of the identity module. So you take in this formula, you take age A to be 0 and N to be 0, and then plot it, and then this is this line. And this has degeneracy 1, because and then the next one in this is the module of the magnetic field. So you put 1/16 here and 0 here, level 0, and that is this line here. And the next one is the energy density operator, which comes from EJ being 1/2 and N 0. That's this third line here. And then the next one would be like level 1 of the identity, but that's a null vector, so you don't see it in the spectrum. So then the proper next one is the level 1 descendant of 1/16. So you put 1/16 here, 1 here, and then you get this line. And then this one, actually, this is the first descendant of the energy density, and this is the second descendant of the identity. If you keep going, you will see the degeneracy, but it gets messy. So yeah. But you have to be careful, because if you have a minimum model, you can have null vectors. You can have null vectors, so you have to project them out. But I mean, you can read. So these numbers you can read of the characters of the module. Okay, but yeah, they are known numbers. Like you must be able to count those if you go higher. Well, actually, one of the next steps is to extend this to higher volumes and then count really them. Okay, and then just to conclude. So it seems that Cardy's ansatz, well, actually it's not seems, it's kind of clear that Cardy's ansatz captures the energy density of massive perturbations of conformal field theories, and then it also seems that it also captures the left-right entanglement entropy of the state itself. And then you can go further, and then not just the left-right entanglement entropy, but the left-right entanglement spectrum also matches very well. And this is actually a new application of this truncated space approach method. And there are some questions that we have to study. So, well, of course, in this talk I only showed like 2 perturbations: this E8 and this tricriticalizing plus 3/80. But you can play with any kind of perturbation, like because you can generate any matrix elements of any operators in the CFT. So you can play with anything that you want. And what I see so far is if you take perturbations which are less relevant, like this result for the entanglement entropy is not that impressive. But it can have 2 different explanations. So it can happen that you have to go to higher cutoffs in the TCSA because maybe it's just not enough the number of states that you keep. Or the other possible explanation that actually this ansatz is getting worse and worse if the perturbation is less relevant. And then if this is the case, then like there is the question like how to fix this problem. There is also another thing that you can study is time evolution. So as I told you, like you take your favorite initial state and then you time evolve with this truncated Hamiltonian, and then you get some time-dependent state, and then you get the same quantity, and then maybe it has some very interesting behavior. I don't know. I really wanna study that. And then, of course, this is another question like, is there any way to get this left-right entanglement entropy from other type of calculations? Because what people do generally, let's say on spin chains, like is this usual space-like separation. And then if there would be some other approach to get this left-right entanglement entropy, that would be very nice. So thank you for your attention.